So welcome to this webinar about large language models and Wolfram Mathematica and the Wolfram language, and how both technologies hope can benefit from each other. My name is 𝗟𝗏𝗃𝗏, and I'm a member of the Wolfram support team here at 𝗟𝗏𝗃𝗏𝗃. And I want to briefly introduce my company and Wolfram for those of you who are not familiar with us. So 𝗟𝗏𝗃𝗏𝗃 is the Austrian reseller of Wolfram technologies for over 2 centuries now. We are based in, for over 20 years. We are based in 𝗟𝗏𝗃𝗏𝗃, Austria, 30 kilometers east of Linz. And besides being reseller for Wolfram technologies, we are also developing software with simulation and data science background, mainly for industry, but also for the finance sector. Wolfram Research, on the other hand, are the makers of Mathematica, the Wolfram language, obviously a cloud solution, Wolfram Cloud, 𝗟𝗏𝗃𝗏𝗃, and also System Modeler. They are based in Champaign, Illinois, in the United States, and they were founded by Stephen Wolfram over 35 years ago in 1987. The agenda for today, there are two main points. At the beginning, I want to introduce large language models, how we can work with them, and important aspects which we should know, like word continuation, the temperature, and tokens. Then we will have a brief look on the strengths and also on the weaknesses of large language models. And in the second part, I want to show you how we can combine computation and large language models, specifically the Wolfram plugin and ChatGPT, and how we can use the large language models out of the Wolfram language. Well, let's start with large language models. So large language models are by now huge artificial neural networks, which are based on a so-called transformer architecture. In 2023, there are many different models on the market. The biggest ones are from, obviously, from the big software companies like Google, Meta, Facebook. For this talk, we will focus on one specific, the GPT model, which is the short notation for generative pre-trained transformers. This was published by the company OpenAI, which is also known for ChatGPT. And we will focus on this one because it's the only one which is currently supported by Mathematica. But one has to say that all commands usually start with LLM, which is because Wolfram wants to be agnostic for large language models, and they will add support for different other models later, they told us. Looking on GPT in particular, from the historic side, GPT-1 was introduced in 2018 with around 117 million parameters, and it was trained on only 8 million web pages and had a token size of 512. By now, we have the version 4 of GPT in 2023. This model has around 1.8 trillion parameters, so a huge, larger amount of parameters, an increased token size of over 8,000, and it was trained on approximately 1 petabyte of data. Keep in mind the bold data here are only assumptions, since OpenAI didn't publish any data on the parameter size or training data size since GPT 3.5 Turbo. ChatGPT, usually everyone is talking about ChatGPT. ChatGPT is the name of the service you can use on the web page from OpenAI, and it was originally based on GPT 3.5. Currently, if you have a non-paid subscription, you can use GPT 3.5 Turbo, or if you have a paid subscription, you can use GPT-4 as well. So how does such a GPT work? GPT models in general are always fundamentally trying to produce a reasonable continuation of whatever text it's got so far. So it tries to give you the answer to a question, the explanation that follows a statement, a response that follows an instruction. And I can give you an example. ChatGPT 2, so the second version, was open sourced by OpenAI, and from its size, it can be run locally on a standard computer. and it's available from the neural net repository from Wolfram. So you can just use the net model command. The neural network is called GPT-2 Transformer trained on web text data. It has two different tasks, and in this case, we want to use the task language modeling. If you execute this the first time, Mathematica downloads roughly 0.5 GB of data on your hard drive, so it takes a couple of minutes. But then it can load this model quite fast. We then can give to the model a request. In this case, give it the beginning of a sentence. The best thing about AI is its ability to, and now the model gives me back usually the most probable continuation, the most probable word which will follow. But I can give it in Mathematica the option, the parameter that I want to get the top probabilities, the 5 top probable words. And if we do that, we get back that the most probable word which continues this text will be learned with a 4.4%, followed by predict, make, understand, and do. And in fact, the model not only calculates 5 words and their probabilities, but a huge number of words. And usually there are only a few words which are in a range with similar probability. With this most probable word learn, we can now do an iteration. That means we just append learn to the request we sent, the start sentence, and then we send this back again to the model. And if we do this iteratively, then a sentence will, or an essay will emerge, which I have done here. So I'm here just doing a string join iteratively with a nested list over 5 times, and I always string join the sentence with the next word the model is giving me, and reiterate it in the model. And if we execute this, we then see after learn, the next probable word will be from, experience, then comes a dot and it, for example. And in this way, a sentence, an essay, whatever you ask a GPT model will appear. And that's the remarkable thing, that when ChatGPT writes an essay, it's essentially asking over and over again, given the text so far, what is the next word? And that's it, usually. Or that's it in this sense. So it's just adding each time one word. And that's also the reason, for example, if you use ChatGPT, the ChatGPT service, that the words appear one after the other, because it's always again reinserted in the model. What else do we have to know about GPT? It's the so-called temperature. If we take always the most probable word, then this leads to rather confusing, repetitive, and flat texts. So that's not really nice. What I did here, I just let the model calculate the next 100 words. And if we execute this, I mean, the same result will appear now. We don't have to read through this. It takes a couple of seconds. But what we immediately see is here that we have here, for example, 2 equal sentences right after the other. And the next sentences even have the same information. So we have here again, the AI is a very good example. And here is again the same sentence. So a lot of repetitive text. And for this, the temperature was introduced, which is nothing more than that we add a statistical randomness in not taking always the word with the highest probability. We can do this with this GPT-2 model by giving the option random sample with a temperature with a certain value, and it turns out that the value around 0.7, 0.8 is a good value to get reasonable good texts, human readable texts. If we have a temperature of null, we always get the most probable words, and if we go over 1.5, then you in the end get at some point you get just garbage. So if you now use this with a temperature, we will get a different text than here, because that's the ultimate consequence now. We added randomness, and this means that that the results are from this time on unpredictable. We always will get a different result, depending on the probabilities of the words the model is calculating. We can do this, for example, here. That's the same example from before, but I asked the model, GPT-2 model, the continuation of the same sentence 5 times. And as you see, I get 5 different continuations. And that's the temperature. For this, the temperature is responsible. And the last thing we have to know about with GPT are tokens. So tokens are the building blocks of text in large language models. A token can range from a single character up to a word in length. And every input in a large language model, every text, every question, every anything you enter in or you give to a GPT model will be tokenized. For example, I have here an example: ChatGPT is amazing. These are 3 words and exclamation mark. But for ChatGPT, for the ChatGPT tokenizer, these are 6 tokens. So chat is a token, G is a token. You can see it down here. The P is a token, is amazing are 2 tokens, and the exclamation mark. I've put down here a link to the tokenizer so you can try this out. And the important thing is that in every GPT model is a token limit. We've seen this in the table before. And the token limit restricts the number of tokens which the model can process as input with every iteration. And this is done to ensure efficient performance. So in GPT-3, the standard GPT-3 had a token size of 4,096 tokens, and GPT-4 doubled that. There you have now 8,192 tokens. There are also models which have 4 times the token size, but they are usually more expensive when you run when you use them. Yes. And now the important thing is memory and context window. If you have a conversation, for example, like with ChatGPT, the entire conversation, the entire one from the start until to the prompt, is always passed to the LLM to get the next word, as we have seen before. So if a conversation is longer than the token limit of the model, the conversation will be truncated and probably important information will be lost. And that's called the context window. So the context window of an LLM starts with your current prompt and goes back in history until the token count exceeded, and everything else before that doesn't happen to the is not known to the LLM. But it means that also means, for example, if the large language model writes an essay for you with GPT-4 and the essay is longer than 8,192 tokens, the LLM does not know that it has already written in the beginning. So that's the short-term memory, so to say, for a large language model. And you always have to keep this in mind if you work with a GPT model. So what are the strengths now of, in our example, ChatGPT-4? If you have used it, you have probably felt, well, I'm almost talking to a real person. It's like an artificial intelligence a little bit. So it has an appearance of intelligence. You have really human-like interaction. If you talk to it, as I said, you think you're talking probably to 1 person or 3 persons at all or more. And you have this large language models have really a large knowledge due to the huge data they were trained on. So you can ask ChatGPT for whatever you like, and most probably you will get a nice suitable answer most of the time. And I just want to show you an example for those who have not used GPT-4 before. So I'm a physicist, and I thought, well, let's talk about black holes. Black holes are interesting. And I told ChatGPT, tell me something about black holes. And then you get a nice overview. You get what's the definition, how they are formed, what are the different types, something about relativity, and so on. And then I thought, well, just give me a short summary. That's too long for me. And certainly, ChatGPT is very polite, so it's a friendly person. It gives me a six-liner about black holes. I'm from Austria, so I thought, well, give it to me in German. And also this task was nicely fulfilled by the large language model. And then I told it, well, I need it for that the child can understand this text. Then, yeah, here we have, for example, a big vacuum cleaner in it. So it compares a black hole with a vacuum cleaner, and that's good to understand for children. And at the end, I said, well, I'm not an astrophysicist, but well, transform the text so it's suitable for an astrophysicist. And also this task was pretty nice, was good, fulfilled by the large language model. So it's really astonishing what it can do by just calculating always the next probable words. So that's really very, very astonishing. So let's switch back to Mathematica. So these are the strengths, obviously, because that's what it was trained for. But there are also a few weaknesses, and I just want to point out 5 of them. You can have the impression that these large language models are intelligent, but if you ask them, for example, something about logic, then they can fail. A simple example, the question is, Alice is older than Bob, or Bob is older than Charlie, and Charlie is younger than Derek. And the question is Alice older than Derek? And if you think about it, you cannot make a conclusion about it because you don't have a connection between Alice and Derek. And usually you get the correct answer from a large language model for GPT-4, but if you ask it 2-3 times, you maybe get this conclusion. You get a nice summary of what you asked it, and in the end it tells you, well, Alice is indeed older than Derek, and that's obviously wrong. So LLMs have a problem with logical thinking. Complex rules also can be a problem. So you can ask ChatGPT-4, what's 6 + 8 divided by 3? And it can solve this without a problem. And from the answer, you get the impression, well, that looks like it's really doing this calculation. But in the end, it's doing word continuation. You have to keep this in mind. The result is correct. That's true. But if you make it a little bit more complex, and I increase the complexity by just increasing the numbers to add, then you can get a quite strange formatted result. And even more, it's wrong. So these are just the numbers I put in there, and if I compare them in Mathematica, you see that already starting here from the last 3 to 6 digits, it's already wrong. It's already wrong. Or for example, what else you can, where it fails is a little bit more complicated. I just asked, what is the integral about x to the power of 3 times the cosine of 2 times x to the power of 2? And then ChatGPT gives this really nice summary that this integral is not elementary. You have to use substitution to solve it. Gives you how to substitute it, and then in the end it says, well, you can recognize that this is related to a Fresnel cosine integral. This is also not elementary. You have to look this up in tables, or you can use software to get a numerical answer like Mathematica, MATLAB, or Python SciPy or something. But if I have a closer look, you see that there's something wrong down here, and even more, if you ask Mathematica, it's easily solvable. You can do it by hand. It's not really that complicated. And the problem here is that ChatGPT-4 is really convincing in its answers. So if you don't have a close look, you may think, well, that sounds reasonable, and if you trust it, then yeah, you can have a problem. Obviously, not a big problem, but obviously due to the context window and the token limit size, you cannot work with big data in large language models. The easy example here is I just give to the large language model 4,000 different numbers and said to it, well, give me the last one. Since the last ones were truncated, the answer was simply wrong. So the last one would be here 10, and I got back 8. You have to keep this in mind. Big data, although it was trained on really huge big data, it cannot process big data. And even this request took a couple of seconds to give me the wrong answer. Reliability is also a problem. If you ask ChatGPT-4 for facts, for example, then it may happen that you get different answers due to the fact that this is a statistical process. For the example here is simple. What's the distance between Vienna and New York by plane in kilometers? And correctly, it tells me, well, I can't tell you because planes are always flying at different routes. But if you use the Great Circle distance, so the distance on the Earth's surface, then it's around 6,800 kilometers. And if you ask it a couple of times, you get always different answers in different sentences. But most of the time you get 6,800 kilometers. But sometimes then you get 6,700. It's just a simple example, but keep in mind, in the end, it's a statistical process. And if two numbers like 6,800 and 6,700 are close in the probability, then at some point this value will change, and you cannot find out whether you can only find out by trying it out. So this is also a problem. And probably one of the biggest ones is that ChatGPT-4 or any model, since they're trained models, they do not have access to actual data. So I've tried one example out here where I asked the ChatGPT-4, what's the current distance to the moon? And obviously it can't answer this question. It can answer what's the closest distance and what's the farthest away distance between Earth and Moon. And that's it. Or for example, if you ask ChatGPT who won the female world soccer championship this year, it will tell you, well, I cannot tell you because my training data ended in September 2021. And that's also the end of the knowledge of ChatGPT. So everything which happened after the training, ChatGPT is not aware of. And we will see how we can later on how we can inject actual data in such a large language model. So how can we overcome some of these problems? You have a textual input in large language model, and in the Wolfram world, there's also a software which takes text as input, and that's Wolfram Alpha. If you have, I've here a short sketch how it works. We will see it in a minute. So you have an input field where you can put in your question, and Wolfram Alpha then tries, because language has grammar, it tries to transform this textual input in some symbolic representation. And then there are rule-based algorithms, computation, there are multiple databases, there's real-time data which Wolfram Alpha can use, and with all this information, it tries to calculate some sort of result, and it presents it to you via a report on the web. So this is some sort of symbolic AI. And we can try it out here. So if we ask Wolfram Alpha, what's the distance between Vienna and New York by plane in kilometers? It will first tell us what its interpretation is, what we wanted to ask. And it thinks, well, you wanted to ask me the distance between Vienna and New York. Then it assumes New York is a city and it's in the United States, and Vienna is in Austria and not in Virginia. And then it's doing its calculations, and we get a calculated result, which is 6,813 kilometers. We then get it in other units, as well as a nice graph, what's the closest distance. So in some way, it would be nice to connect these two worlds, because these two worlds, Wolfram Alpha and large language models, are a little bit like this outdated view of our brain. In former times, we were thinking that the left-hand side of our brain is important or is doing all the logic stuff, math, physics, and all this stuff, and the right-hand side is responsible for our creativity, language, music, painting, and all that stuff. So it's similar to Wolfram Alpha and large language model, and it would be nice if we could connect them. So we don't make an artificial intelligence out of it, but we can give the large language model and Wolfram superpowers. And the first thing I want to show you is the Wolfram plugin in ChatGPT. So Wolfram was one of the first companies that worked together with OpenAI to develop a plugin so that ChatGPT can is enabled to ask Wolfram Alpha questions and can retrieve the answers, and then use these answers to use them as facts in its response. And you can, if you can use ChatGPT 4, then you can enable the plugin shop or the plugin store, and there you can install for free the Wolfram plugin. And when you then ask ChatGPT for what's the distance between the moon and Earth, then you will get an exact distance. In this case, when I made this conversation, it was 361,261 kilometers. In addition, you get also a nice graph presented, which shows you the distance of Earth and Moon over time. And you always get the information that ChatGPT used Wolfram to retrieve this data. So with this, ChatGPT is able to retrieve real-time data and curated data from Wolfram, and it's not guessing anymore, if you want to put it this way. The other way is when we use large language model out of the Wolfram language or Mathematica. For this, we need the most recent version, which is 13.3, and you need an OpenAI API key. So the first time you execute an LLM function, a window will pop up which asks you for the OpenAI API key, because all these requests are sent to the OpenAI servers, are then processed through their large language model, ChatGPT 3.5 or ChatGPT 4, and then returned back to Mathematica. I put in here a link to the support page. If you have problems with entering the API key, this support page will help you. In addition, what I did here is I made a new configuration over the default configuration. The default configuration for the large language models is stored under $LLM evaluator. And with LLM configuration, I can now store a configuration, and I want to use ChatGPT 4 for the rest of this talk. Otherwise, ChatGPT 3.5 Turbo would be used. And with this, we can start. In the agenda, you saw that we will talk mainly about 5 different commands. The first one is LLM synthesize, and it's the workhorse for using LLM. It's simply put, it generates text that continues the input prompt. That's it. So what we can do, LLM synthesize, and then, for example, as I said here, well, I want a short poem about a fish in 4 lines, and then this prompt or this request is sent over to OpenAI, as we see in the little box. The response or the completion is received, and well, that's the completion, and it sounds like a little short poem about a fish. It's true. I can give a parameters to LLM synthesize. I can ask not for the completion but for the full text, so I will get the prompt as well as the request as well as the response. And sometimes it can take quite a time because we are now depending on the servers of OpenAI. And here we have the request I sent over and the answer, which is again different to what we got before due to the temperature. What I can do as well, I can make a new configuration instead of my default configuration. In this case, I have to use, with LLM synthesize, I have to use the LLM evaluator option. And I can give it an association. Again, I use the GPT-4 model, a temperature, I decrease the temperature to 0.5, and I give it a prompt. And prompts are simply texts, is text which is put before your request. So in this case, I say, well, always answer in German. And if we have, again, I ask for a full text, so I will receive back the request as well as the response. And the request now is the prompt, and on the prompt appended is my request, and the response now is obviously in German. And that's usually how prompts, how we will see it later on, how different things work when we work with large language models. We can store this configuration in a variable with the LLM configuration, which we have already seen before, and then we can easily use it afterwards with the LLM evaluate option. Yes, so we will see this LLM synthesize later on a few times. There is also LLM function. LLM function now represents a template for a large language model prompt. Just give you an example. So you have LLM function, and you input here just a Wolfram language template. And here I have 3 arguments or 3 parameters I will have to give to the template, and they will be inserted here in 1, 2, and 3. What I will input here is on the first place exciting. So we write an exciting summary of Microsoft's share price yesterday, giving the following facts. And the facts, so the parameter 3, will be this command. So what I'm doing here is I'm retrieving the financial data. That's a service from Wolfram, where I will get the financial data from yesterday, and I'm asking for the share data of Microsoft. And OHLCF means the open, high, low, and close value of the share, and the overall traded shares, the amount which was traded on yesterday, or the most recent data. And I made out of this an association, and this will look like this. And this will be put in number 3. And with this, I do a direct fact injection, so to say, for the large language model, because I give the large language model in my request the data it should use for its response or its completion. And in the end, we have here the full command. So the finite story is this LLM function up here. And then I give it 3 parameters, exciting and Microsoft, and the association we have seen before. And the result is a rather thrilling performance. So it's exciting, and as you can see, the values which are in here are just the values which I gave it in this 3rd parameters for the facts. And in this way, we can directly inject within the context window of 4 or 8,000 tokens. We can inject recent data or facts into an LLM. What else can we do? We can also produce computable results. LLM function has a parameter where we can tell Mathematica which type the response will be. In this case, I ask for a city on the way between parameter 1, as argument 1 and argument 2. And I say, and I tell Mathematica, well, the response will be a city, it will be an entity city. And I do this, if I do this, for example, if I'm asking for a city between New York and Chicago, I will get back Cleveland, but not the string Cleveland. Mathematica transform this city in an entity city, which is Cleveland in Ohio in the United States. And then I can use this information in Mathematica, for example, just make a geographics out of it and get a nice map. I can go one step further. If I, for example, need a list of cities, I can say, well, I need a semicolon separated list now of cities between this argument 1 and argument 2. And then the result I'm expecting is then, for example, a delimited sequence of cities, and the delimiter will be a semicolon. And again, I ask for cities between New York and Chicago. And in my case, this fails because the input Mathematica receives is of this form. So we have New York, Philadelphia, Pittsburgh, and we always have the state following the city name. And for some reason, Mathematica cannot transform this information into an entity. So the only thing I can do is I can ask the large language model to give a different, to give the result in another format. And I did it. My first try was just use a sole semicolon separated list. I just added this one word, and then I get a list without the states. And that sounds good. So I tried it again with my first LLM function, and I will get back a nice list of all these cities between New York and Chicago, and then I thought, well, make a geolist plot out of it. And then I got this, and I thought, well, that's not what I was expecting, because Toledo is in Spain. So actually, we will need the state information. So again, I have to reformulate my request, and I want it in the form city state. And with this, I finally only get, I don't know why I get only 4 cities, but again, I get the city Toledo, and now Toledo is in Ohio, and it works. And we get a nice geolist plot. So what I wanted to show you with this is that you always have to try how to convince the large language model to give you the response that you are expecting. Even more, there are a few other things you can do. For example, you can now use the common sense knowledge which was trained in the large language model. A simple example, but astonishing. For me, it was astonishing that this works nicely. I declared an LLM function where I asked the large language model, if argument 1 is bigger than 2, return 1, otherwise return -1. I say, well, the result will be an integer, and here I in addition used the LLM prompt function with the argument numeric only, and this should ensure that I really get only a number back. And if I use this on the 2 arguments elephant and turtle, I get the result back. The answer is 1. So an elephant obviously is larger than a turtle. But what can I do with this? There's the sort functionality in Mathematica. And if I sort, for example, worm, elephant, atom, and moon, then Mathematica will sort them by alphabetic order, A, E, M, and W. But this form up here, this LLM function, is exactly the way I need it to put it in the sort function as sorting algorithm. And if I do this now, so again, I have the sort command, I have the list of worm, elephant, atom, moon, and a second parameter, I give the sorting algorithm. And now, if I execute this, during the sorting, OpenAI will be called approximately 6 times due to the sorting algorithm. And now the sorting happen independence of the answers of OpenAI. And now they are sorted by what the large language model thinks is the bigger one. So the moon is bigger than the elephant is bigger than the worm, and the worm is bigger than the atom. And that's hard to accomplish in another way. So that's a nice example, I think, what one can do with large language models besides language. We have seen before the LLM prompt command. With the LLM prompt command just gives us a template object for a specified large language model prompt. And what that means is we have already seen the large language prompt numeric only. And the only thing this command is doing, it has a content, and the content is just 4 sentences. And these 4 sentences are again put before my request in the message which is sent to the large language model. And let's go on. There's another prompt like 𝗟𝗏, which is a prompt which where you ensure that the answer is that the large language model answers the question as if the listener is just a 5-year-old child. And again, this prompt is just put in front of your request. But there are also prompts that have parameters in it, like the joke suggest prompt. And if one has a look at the content of this joke suggest prompt, it has 2 parameters. The first parameter is the content that you want to work on, and the second one is in this example here, that you want to write a joke in some sort of style. So if you use this LLM prompt joke suggestion and you just give 1 parameter, you get back the prompt, the full prompt, and there is a default style, for example, which is knock knock. But I can give also a style like here ice cream, and then this prompt tells the large language model that I want to have a joke about ice hockey in the style of ice cream, and it should not be sexist, racist, homophobic, and so on. So So if I put this in LLM synthesize, I in the end will get back a joke about this. And that's about LLM prompt. And there's also the LLM resource function, which just combines these two commands in one function that I don't have to call them all the time together. There is a Wolfram prompt repository from where you can download a huge amount of different prompts like pirate speak or cheerleader or the tech support bot, and the answers from the large language model will be then in like a tech support bot. So you can try them out easily. You can even send your own. If you design a prompt, you can send them to the prompt repository so that is other people can use it from there. We've already heard something about fact injection, direct fact injection, but there is also indirect fact injection, and that's the command LLM tool. What is LLM tool doing? In this example, I have a tool where the LLM should be able, if it give me the name of a city, it gets back the population. So you have the command LLM tool. The name of the tool is city population finder. The parameters I need, the tool needs is the variable city, which is in Mathematica the entity city. And with this entity, I can easily give back the population. And I can save this in a variable tool. And then I can give this, here we have again LLM synthesize, and I can give this tool to the large language model via the configuration, via the option LLM evaluator, and in an association with the key tools. I just give it a tool. And then the request, I say, well, use the tool to write, for example, here, to write a few sentences about Chicago. And in this example, I want to get back all information, and I save it in the results variable. And usually, if I don't use this option, this parameter, like all or full text or what we've already seen, then usually I get back the completion text, so the answer. And the answer here is a nice little, a few sentences about Chicago, and here we have an exact number of people. So the interesting thing is, well, first you can have a look in the results, in this association, which is stored in the results variable, which keys are in there. And there are, for example, is the full text that we have already seen, completion text we have already seen. But what's interesting is, in this case, prompt text and completions tools text. So in the prompt text, we can have a look what was sent over to the large language model. And we immediately see that the first sentence we see here, it's not use the tool to write, but it's something different. The first 4 sentences are generic sentences from Mathematica, where it tells the large language model that it can use a tool and that the tool takes JSON schema as input. And then it describes the schema to the large language model here. So this is the name of our tool, the city population finder. And down here we have the input variable, which is a city, which is a string. Then it tells the large language model how it can call this tool in a really general way. And in the end, it tells the large language model where it can find the result. And then in the end, here comes the request I wanted to send over. So everything else before was auto-generated because I used the LLM tool function. And if we have a look at the completions tools text, we see that indeed the LLM called this function in this way. The city population finder, the variable is city, the value is Chicago, and here is the result from Mathematica, 2.746 and a few other million people. And then the large language model is using this number in its response, in its completion. And it's an indirect fact injection because it can happen that the LLM doesn't use the tool and just responds with a value it assumes. So therefore, that's an indirect. You cannot enforce it. You can enforce it somehow by your input, but in the end, you always have to have a look whether it called it via this completions tools text. And you can even go a step further, but this one doesn't work all the time, but it's also very astonishing. What I tried here is I give now ChatGPT a tool with which it can run Wolfram language code. So I don't write the code myself. I tell ChatGPT to write the code. So in this tool, the tool is just called run code, and that's a description for it, so that the large language model can understand what this code is doing. This tool is doing the only variable is code, and since this code will be executed on my machine, I will get first the choice dialog to see the code, and then say, well, yes or no, because probably the large language model sends code to my machine, which is not really nice. And if I say yes, then the code is transformed to an expression, to a Wolfram. It's a string, so it has to be transformed to a Wolfram language expression. Is then executed, and then you have to convert it back to a string. And again, the same thing. I call LLM synthesize. I give the configuration, the tool via the LLM evaluator option to the LLM synthesize. And now I ask the question, which is closer to Boston, San Francisco or London? Use the tool as you write your response. And the completion text is a little bit confusing. So the answer is, according to the calculations, the distance between Boston and London is approximately 5,279 kilometers. Therefore, San Francisco is closer to Boston than London. So there's somehow missing what's the distance between San Francisco and Boston. But when we have a look at the completions tools text, we see that the large language model called this function 2 times. And the code is real Mathematica code, so it called geodistance of the entity value of the entity San Francisco, and the entity value is position, and the second entity is Boston and the position. And this calculated to 4,350 kilometers as a result. And then it executed a second time the code with London and Boston, and got back 5,279 kilometers. And then it made the correct argument that now San Francisco is closer to Boston. But the code which was run was written by the large language model. Since the large language model does not have a compiler, it can also happen that you get a code which will not execute because of failures in it. But well, that's also really impressive, I think. And last but not least, the last function we will see today is a function for data extraction. Large language models are really, really good on extracting data. You need huge amounts of data to train them, but they need really not much data to extract data out of text. And I also want to show you just a simple example. So you use the LLM example function, you give it a list of examples, and these are rules. So here is the input. The input in this case is John, is a 52-year-old male who is 6 feet tall. And what I want to get back, that's a string representation of an association in Mathematica. And I want that the name John is labeled with name, that 52-year is labeled with age, but it's a quantity 52 with the quantity year. And the same I want with the 6 feet tall. I want that it's labeled with height, and it's a quantity of 6 of the type feet. The second example just is Fred, who is 1.7 meters high, and so the age is here missing. And here I tell just the LLM what I expect it to do if a value is missing. And in the third example, I show the LLM what it has to do if you have, for example, 2 names with 2 ages or 2 heights. Then I want to get back a list separated by a comma. And with this simple example, I can now ask the LLM, well, extract me the data out of these sentences. And in this sentence, I have John Smith, who is nearly 70-year-old. His wife Kate is 1 meter and 78 centimeters, and since John is 180 centimeters high, she's smaller. And the result is exactly what we expect, or what we read out of this text. And in addition, since we told the large language model that we want the numbers to be quantities, we can now, for example, unit convert the numbers in it. So here I just unit convert the height of John Smith in millimeters. And we made, in this way, numbers, for example, computable out of text. Yeah, with this I come to the last slide. Everyone is a coder now. So we have already seen that large language models are quite good at code generation. So you can, for example, if you ask ChatGPT simple question, how can I import the CSV file into a dataset in Mathematica, then I will get a tutorial more or less get generated for what I need, and that works really well. For simple tasks, you can ask the large language model even to write you more complicated algorithms, but then it can happen that they are not correct. I mean, you can do that for Mathematica, for Python, but it's really nice if you have a problem, a small problem, and you don't know how to solve this, then you can ask a large language model as starting point. And Wolfram thought, well, that large language model is like the interface is like a notebook interface, and it would be nice we can integrate this in our notebook interface. And for that, they created the so-called chat notebook or chat-enabled notebook. And here you have an input prompt like in ChatGPT, but now in the context of Mathematica. And here I can, for example, just write simple questions, or I can write questions to the large language model. For example, like plot the differences of consecutive prime numbers to 500. And then I get a small explanation how we can do this, and even more. It shows me how I can plot this, so I get a really nice tutorial about this. It then executes what it thinks is good Wolfram language code, and in the end we should see a plot generated. And here we can have a look at what's the code, what exactly is the code. And I even can then go a step further and ask whether add, for example, add a moving average with a window of 10 to the plot. And so for exploring new functions or doing other thing, this is really a nice way of interacting and learn the Wolfram language. And finally, hopefully we will see a plot or not. And here is a plot. The only thing which is not really what's not correct is that I asked for a plot size for the first 500 points. It's out of first 500. It's okay. Okay. Yes, and with this, actually, I want to end this webinar. Hopefully, I could show you that ChatGPT and Wolfram, it combines fluency and accuracy. And I want to thank you in the end for your attention. And well, if you have questions, Then is now the time for questions.